So today let's explore this insulation tester. It was donated by a viewer, so big thanks for the donation. It comes in a nice leather case, and let's remove it from it if I can, because it's sort of falling apart. This is old, probably from the 80s or maybe even 70s. And the point of it is to test insulations, to measure their resistance. And it seems that this one can use for the test from 100 volts all the way to 1000 volts. Selected using this switch, and it has 3 ranges. One is in kilo ohms and the other 2 are in mega ohms. There is an analog meter with 3 scales, kilo ohms, mega ohms and another mega ohm scale. And here is the on button, which doesn't stay in, but I guess it's not a failure. It's meant to be like this, to prevent you from forgetting it on and discharging the batteries, and also to prevent you from getting a shock from the terminals. And if you get a shock, you jump off the button and it turns off. Here is some calibration, zeroing potentiometer, and it has 3 terminals here. One seems to be common for the ranges, and I guess this one is for the kilo ohms and this one for the mega ohms, depending on which range you select here. And this thing doesn't seem to be in the best condition, but of course I'm not complaining about something donated, but it seems to be dropped, and this is not from the shipping, and there was no big chunk of plastic in the box, so this was already broken before the shipping, and of course maybe the shipping made it even worse. It was actually held together using a lot of screws, but all of them are actually broken now. But the worst thing is, I guess, this analog meter seems to be stuck. When I turn it around its axis, the needle should be moving, but it's not moving, it's stuck here. And this also doesn't seem to be from the shipping, because he sent me a picture of it and it was already about in this position in the picture. Of course, normally the needle of the analog meter with no current in its coil should be here, even though maybe the meter is backwards and the zero should be here, because basically the less resistance, the more current it passes, so maybe the needle actually goes to the left with more current. And it would also make sense, because typically a potentiometer calibrates the meter at the maximum point, and this physical knob calibrates it to the zero current point. I don't even have to remove any screws to see what's inside of it. There are various switches in it for all the ranges, and they're interlocking using this metal bar. And this one is cut out here, so it's actually intentional that this one does not stay in. And here's a potentiometer for the calibration. Seems like a double potentiometer with some resistor on it. And of course, here are the batteries. And it doesn't seem to have any type number other than XS. Good luck trying to Google the schematic of it. Well, if you try to Google XS, it will probably show some clothes in a size that's probably illegal now, because it would cause burger eaters some psychological damage. So instead of Googling it, we have to figure it out somehow. I don't see any point trying to turn it on before disassembling it because of this broken meter. The needle is stuck, and if I turn this, it actually moves, but it doesn't move like this. It should. So let's check the batteries and then open it. Here's the battery space. Let's unscrew the screws from it and see the batteries. Hopefully not completely rotten and leaking everywhere, which is quite typical for old devices. And it says battery R20, 7 times 1.5 volts, 1.5 amps maximum current. It seems to be a little bit rotten here. And it seems like these cells in it, 1.5 volts, made in Hungary. Some maker, probably something in Hungarian. I also don't understand this. 6.30 FT plus. And it seems to be dated 1981, the 5th day of some month, which I don't understand in Hungarian, of course. And is it the production or the expiration? But in either case, it's bloody old. It's not even leaking much, surprisingly. Very old school batteries. I would expect the batteries over 40 years old to be more rotten than this, actually. This is a nice surprise. Some small spots on it. All of them seems to have the same date on them. It's dirty here, but it doesn't seem to be a liquid. It's good. Of course, this foam is completely rotten and falling apart. Surprisingly, the contacts seem to be quite clean, not rusted or corroded. Nice. No contact corrosion from leakage in more than 40 years, compared to something like Duracell. And I guess there are some screws going from this side, but I don't really see any point unscrewing them. Is something under this? It's not a screw under it, it's just a hole. I'm trying to turn this screw which has nowhere to go. A poor homeless screw. Well, let's just open it like this. You can see the switches at the bottom here. And there is a transformer. I guess there is some inverter. 2 power transistors with this transformer probably make some inverter. And it's an iron core, not ferrite. So I guess the inverter runs at quite a low frequency. Maybe just a couple hundred hertz. Definitely not many kilohertz. Some 1 kilovolt, 150 nanocapacitors. Probably smoothing the voltage from the inverter, which goes up to 1000 volts. I guess there is not really that much to it. It's an inverter with 2 transistors producing from 100 to 1000 volts and a couple transistors, and then it's mostly just some resistors and calibration potentiometers. And the principle isn't really that complex, but it looks more complex because it has more ranges, 4 voltage ranges and 3 resistance ranges. But at time it's probably using just some of these potentiometers and resistors, definitely not all. I guess 3 potentiometers here calibrating the 3 resistance ranges and 4 potentiometers here, adjusting the 4 voltage ranges here. Can I completely open it somehow? And of course this analog meter is completely disintegrated. Of course the broken plastic bits could be glued back, or you could stick some piece of new plastic over the hole, or you have a lot of sticky tape if you're desperate, but not sure it's going to be repairable with this smashed meter. This thing probably completely comes off. And here's the magnet, which is also loose in it. There is some coil with a wire going to it. Not sure where's the other. And the blue one is probably going to the other side of it. How am I supposed to completely open it? Am I supposed to unscrew the switches from the front panel here? Because the wires are quite short and going from here to somewhere here. You have to get the meter out to see if it's repairable, because if the meter is not, then the entire machine is not worth any repair effort, of course. This is also held in place using some wedges or whatever that is. It pops out. Of course, this is very easy to break if it's not broken already. It's on 2 wires and it's rubbing. Let's document where the wires go and let's cut it out before I damage it, and let's explore the rest of it, and then let's try to fix the meter. There are these stands. I guess when it was assembled, this board was actually part of this side and then the back on this. But because it was broken, I opened it in the wrong order. Here are the connections between the batteries. It seems like 3 connections. So the battery had some tap on it. It seems like the red one is the positive of all batteries, the blue one is the negative, and the black one is like 1 battery below the main positive. 1 battery voltage lower than this one for some purpose. And the total voltage of the batteries was 10.5 volts. But it's split into 9 and 1.5 on top of it. And the board has just connections here, no components. And here there is a lot of components. Here's, I guess, the inverter, some diode for rectification, high voltage resistor, power transistors, but no heatsink. It's probably not a very powerful inverter, just for the sake of measuring something. Some small transistors, 3 small ones. I guess if you're measuring like 5000 mega ohms, the current is so low through this resistance that you have to amplify the current before it goes into the meter. And there's a special double potentiometer which says 5.6 kilo ohms plus 10 kilo ohms. So it's 2 potentiometers and each of them is different. And it's dated 1978. And both of them are 1 watt plus minus 20%. Nice. And here are the switches, which I probably didn't have to remove, but anyway. And here's the meter. And the last division on the highest scale is 5000 mega ohms, quite a high resistance. It actually changes based on what range you select. For 500 volts, I guess you're reading it directly, but for other voltages you're reading it with some multiplication factor. So when you, for example, select 1 kilovolt, you're multiplying it by 2. So if it says 5000 megaohms, it's actually 10,000 megaohms. Can we somehow fix it? It's a big magnet with a rotating coil in it. I guess some dampening mechanism so it doesn't oscillate too much. Here's the calibration, which basically moves the entire thing. It actually moves when I move the calibration lever, but it doesn't move freely on its own. It's rubbing. It seems to be a different mechanism than I expected. There is no hairspring and no needle bearing. It seems like there is a string going through the center, and this string, not a spring, actually works as a connection but also as the return spring. The string goes from this springy piece of metal, which is also the electrode, the negative. It goes into the coil and also gives it basically a support. It's probably its bearing. And on the other side it looks like it's barely visible, it's very thin. And this string is actually broken. The string coming from this springy metal, which was the positive terminal, and I guess it was going into the center of this hole, supporting the shaft. And this doesn't really seem to be very repairable, unfortunately. It was probably stretched and holding it centered in the magnet, but now it's of course off center and rubbing, and also have no electrical connection and also no return force. This is not going to work. Measuring the resistance between the wires and it shows open circuit. You're gonna see the string still intact on this side, but here it's broken. I don't think I can fix this. I can try to disassemble it and see. I'm trying to take this one off and some piece of plastic is falling over here. This is hopeless. There was this thing on it and this springy washer on it, and this plastic is disintegrating now. This is the string holder and the contact basically, and through it the string went into the hole in the center of the moving coil mechanism. And because the meter is broken, I was looking at some other meters I have. Maybe I can stick some other into it, even though of course the scale is not going to match. But at least let's try to see if it moves or something. And of course each of them has a different sensitivity. And this one is I guess 1 milliamp, very insensitive. The best ones are I guess about 50 microamps. These are 200 microamps. And this one even has a warranty. 1970. Nice. But unfortunately I was measuring these three and they're all open circuit for some reason. So let's try this meter. This one is 400 microamps, not the most sensitive, but it's big and we can just see if it does something. I'm wiring it in. I'm putting 2 anti-parallel diodes on it to prevent it from being damaged if something goes wrong. But in a normal operation the voltage drop never reaches the voltage drop of the diodes. And of course it requires a tapped battery. I don't have 7 D cells, so I'm wiring a double bench power supply into it. It's 6 batteries plus 1, and the bench power supply also has the advantage of measuring the current of the 2 rails and having a current limit if something goes wrong. And here's my double bench power supply. One output is set to 1.5 volts and the other one to 9 volts. My bench multimeter is monitoring the voltages and these meters are going to show the current draw. I'm going to press the on button. Almost nothing is happening. I guess in the kilo ohm range it draws almost no current. Let's switch it to one of the mega ohm ranges. Now it draws more current, about 150 or 200 milliamps. And I can hear the inverter. Pressing the on button in one of the mega ohm ranges does not move the needle here. But I guess when no resistance is connected, it actually is meant to show nothing. The needle is not meant to move. So let's try to short it with a wire and let's see now what happens when I press it. And it also draws more current when it's shorted. And these meters are 1 amp full scale, so it's now drawing about 400 milliamps. And the meter is not moving. Of course I had it at 250 volts and the current draw depends on the setting of the voltage. The higher the voltage, the more the inverter draws. 100 volts, 250 volts, 500 volts, 1000 volts, a bit over 1 amp. Now switch the meters from 1 to 2 amp range. It's about 1.1 amp, I guess. And also the consumption changes based on the calibration potentiometer position. I guess the calibration potentiometer actually changes the voltage of the inverter. Now it's in the 250 volt position, and the potentiometer actually changes it from 218 to 368. And the 100 volt position, the potentiometer can actually regulate it from 89 to 150. And this was of course the mega ohm ranges. Now testing the kilo ohm range, and it's actually putting 1.5 volt into it. This has no effect. It's actually putting the one cell voltage into the terminals for the kilo ohm range. It was basically this voltage. And when I short it in the kilo ohm range, the meter is actually moving backwards a little bit here. Let's flip it so it's the right way. Not really moving much. And of course when the terminals are open circuit, it's not moving at all. Open circuit terminals, shorted terminals, open, shorted. Not much of a difference. Is it possible this one was that much more sensitive? And I also guess it was backwards really. This was with no current and this was with full current. Basically a mirror image of a normal meter. I was wondering why it's not doing anything in the mega ohm range, so I just randomly poked my meter into this capacitor and bloody hell, the capacitor seems to be shorted. I desoldered the one pin to verify it's the capacitor and not something in the board. Shorted capacitor, nice. It's 47 nanofarads, 250 volts DC. So let's try to replace it. I have a 47 nano 1 kilovolt capacitor, which seems to be made in 82, seems appropriate. Measures 48 nano. Guesstimating the dissipation factor using my ring tester. It seems to be just a polyester, but I don't think it requires a polypropylene capacitor. The capacitor's in, set to 250 volts, the high mega ohm range, the mega ohm terminals shorted, and let's see. And it's moving. Nice. And the meter is showing nothing when it's open circuit, and some deflection when it's short circuit. It's basically the other way than the original scale. Now the infinity resistance is here, and the zero resistance should be here. I guess the calibration is done by shorting it and then turning this to get it basically to zero, which was the maximum deflection for the meter. Of course I can't get it to the full deflection because the meter probably is less sensitive than the original. And there is a small electrolytic capacitor in it, 22 microfarads. Let's measure the ESR of it, and the ESR is 1.9 ohms, which is really not that horrible. It should still work, and that's the only electrolytic capacitor in it. And measuring the waveform on the primary of the power transformer in the inverter, and it's about 2.2 kHz frequency, a nice square wave. And it's changing as I turn the calibration potentiometer. And believe it or not, I actually found the schematic of it. It helped to add the name of the maker into the search. And here is the inverter, the two power transistors driving the power transformer. Here is the primary, the secondary with taps, which are switched, a doubler, and there is a switched resistance in series with the terminals, and also some switched resistances in the feedback, regulating the voltage. When it reaches the nominal voltage, I guess it somehow shifts the frequency of it to limit the power. And here's the self-oscillating pair of small transistors with a small transformer, and this drives the basis of the main power transistors. And of course the high voltage from the inverter is used for the mega ohm ranges, and for the kilo ohm ranges it's using just one battery or one cell voltage, 1.5 volts. And all the transistors are actually part of the inverter. There is no transistor in the measuring circuitry. And all of the transistors are PNP, germanium. And the circuit has a common positive, which is quite typical for germanium transistor circuits. And I was thinking some transistor amplifies the current before it goes into the meter, but it's not the case here. And with germanium transistors it wouldn't be possible because the base to emitter junction has a lot of leakage current, so it can't sense a very low current, basically. And the principle is very simple. Either the high voltage or the 1.5 volt voltage, goes via the measured resistance, and then it goes into the meter with some resistive networks. For the kilo ohm range, working at 1.5 volts, it goes via this network, and for mega ohms there is some series resistor, then the measured resistance, and then it goes again via some other network of resistive dividers basically, plus some zener, which is it a protection or is it giving it a more logarithmic scale? I don't know. And there are two resistors switched for the 2 mega ohm ranges, some calibration potentiometers, another calibration potentiometer, and the parallel capacitor. And this is the capacitor which was shorted. And basically the meter was shorted via this capacitor, and that's why it was not showing any deflection before I changed this capacitor. And I guess you're not supposed to switch the ranges while it's running, because I guess these switches disconnect one contact before connecting the other one, and if you switch it while it's running, momentarily there is no resistor connected parallel to the capacitor, there is nothing pulling the voltage down, and the capacitor might actually charge to the full 1 kilovolt. And this is, I guess, how this 250 volt capacitor got shorted. Or maybe because of a poor contact in the switches. When no switch is making contact here, the capacitor can charge to most of the voltage. And of course the inverter is not running for the kilo ohm range, and also the tap on the battery is only used for the kilo ohm range, so when using it for the mega ohms, you could basically just use a single power supply. And of course the kilo ohm range is sort of useless for me because it's basically doing what a normal multimeter does, with way less accuracy than the multimeter. Only the mega ohm range is actually interesting because it's using various high voltages for the test. And the inverter voltage feedback is basically a resistive divider with this upper resistance, this lower resistance, some zener, and when the voltage reaches the nominal level, it's pulling the supply voltage of this self-oscillating base driver down. And unfortunately, it doesn't say the sensitivity of this meter, but I guess it must have been a bloody sensitive meter. The most sensitive analog meter I have seen was, I guess, 50 microamps. Not sure what was this. It has quite a big strong magnet, which probably helped it to be quite sensitive. The torque in it is basically the product of the coil magnetic field and the magnetic field. So if the magnet is very strong, then you need a less magnetic field from the coil. For the low mega ohm range, it's full deflection for zero resistance. And this is showing just about nothing. And for the high mega ohm range, it's 10 mega ohms full deflection. And it's again showing very little. It shows much more deflection when it's shorted in the high mega ohm range, but zero resistance is not even on this scale. Now testing it with the digital meter, it's showing about 6 microamps, and this would have been the full deflection. Is it even possible the meter was that sensitive? This is the low mega ohm range shorted, and this is the high mega ohm range with 10 mega ohms. It can actually be also calibrated to about 4 or 5 microamps. I'm still trying to figure out these resistors and switches here. I guess this is for the low mega ohm range and this is for the high mega ohm range. But it's only conducting above a certain voltage. The voltage drop of this zener, I measured it, it's about 4.5 volts. And this low resistance potentiometer is used for the kilo ohm range. This one is for the low mega ohm range, and in the high mega ohm range, I guess none of these two is connected. Which makes more sense. For the high mega ohm range, it has to be bloody sensitive, so it has no parallel resistors on the meter. Only the 100 kilo ohm one, which is a high resistance, but not these, which are much lower resistances, 2.2 and 10 kilo ohms. And here before this high resistance pad here. When one of these is connected, most of the current goes via a low resistance pad here or here, and very little of it goes via these multiple 100 kilo ohm resistors. And of course the schematic isn't exactly the same version, but at least similar. And I tested all components in this mega ohm range circuitry, and I measured what's set on these potentiometers, and everything seems to be good here. All the components in the device seem good, and I just can't get more than about 6 microamps in this meter. And no matter how I calculate from the values in the schematic, it always looks like the meter was like 5 or 10 microamps super sensitive. And just looking at the high mega ohm scale, it's 100 mega ohms per half deflection basically. And the default range without multiplying is 500 volts. And at 500 volts, 100 mega ohms is going to pass 5 microamps. Which if it was half deflection, the full deflection would be 10 microamps. And this is if all the current was going through the meter, whereas in reality some of it goes through the parallel resistors, which means the full deflection of the meter was 10 microamps at most, probably less. But at half the deflection maybe a little bit of the current is already going through the zener, and about 1/5 of the deflection is 500 megaohms. And this is 1 microamp, 1/5 of the deflection, and at this point the zener is not yet conducting, I guess. And if 1/5 of the deflection is 1 microamp, the full deflection has to be 5 microamps. And the 10 megaohm resistance of this meter should give it full deflection, and it's showing about 5.8 microamps. And the low megaohm range with the terminals shorted again should show full deflection, and it's showing 6.1 microamps. All my measurements and calculations are pointing at about 5 or 6 microamps. Unfortunately, none of my meters is anywhere near this sensitive. So I have to just conclude I have absolutely nothing to replace it. And I really guess this zener is to make the scale logarithmic. Looking at this scale, it's half the resistance, double the deflection up to about here. From here to here, the voltage drop of this resistor and this potentiometer is not enough to make this zener conduct, but from here on, it's logarithmic, because of the logarithmic voltamp characteristic of the zener. Well, this turned into a long, confusing, boring video with quite a disappointing end, but that's life. We didn't fix it, but at least we learned something. And of course, if you've made it that far, please consider subscribing, supporting my channel on Patreon, or using the thanks button. And a big thanks to all of you who already support me. This channel couldn't exist without you. And I wish you a happy new year.